Welcome. Prior to this video, we talked about solving a system of equations in two variables. Now, an equation in two variables generally represents a line, and finding that solution would be the point where those two lines intersect. An equation in two variables could also represent a curve, and you could be looking to solve where two curves intersect at multiple points. In this situation, we are talking about three variables. So what is an equation in three variables? Two variables gives us a line or a curve. An equation with three variables is a plane. So we're looking at a system of equations dealing with three variables, and we may have three planes. Remember, if you have two variables, you would need two equations. Here, three variables, we would need three equations. So the solution to a system of equations in three variables is the intersection of three planes, and it's written as an ordered triple, x, y, z. Now, most of the time, and for what purposes you'll see in this class, you're going to get a point, a specific solution, one unique solution, that ordered triple. But we can have other types of solutions. We could have a situation where we have three planes that are all intersecting. However, you'll notice that they are not all three intersecting at the same point or line simultaneously. So that is a no solution type of situation. You could also have parallel planes. Parallel planes do not intersect, just as parallel lines do not intersect. And again, that would be no solution. And then we have two interesting cases of infinitely many solutions. So you'll notice in this situation, all three of these planes are intersecting on the same line, such as the spine of a book. All of those pages are intersecting. So this would be some sort of situation where we have an x and a y, and then we have some z, which is a function of maybe x plus y. So you'd have an xy expression here for my third variable. And then we could also have infinitely many solutions where they are all the same plane. And in that situation, the answer is a little bit more complex to write, but you have an x and a y in terms of x, and then potentially a z in terms of x and y. You aren't going to be seeing these infinitely many solutions in your homework, but I do think it's important for you to recognize that we have those types of situations. So all of the answers you will see, you're going to be looking for one ordered triple, x, y, z. And how can we find that ordered triple? To solve a system of equations in three variables, we will use what's called a type of Gaussian elimination. Karl Gauss was a mathematician, a German mathematician. So Gaussian elimination, basically that involves using the elimination method twice. So we're going to multiply and add, scalar multiplication and addition. So we're going to do that twice with two different pairs of those three equations to create two new equations, which are both in only two variables. So we're going to reduce the three equations and three variables down to two equations and two variables. And at that point, it becomes easy for us to solve the system using the two new equations from the previous step, using elimination or substitution as we discussed in the previous section. And then we'll get one variable, we'll work backwards, plugging in that one variable to get a second variable, and then using those two variables to get the third. So when we look at solving these problems, we have a few permissible options, a couple of things that we're allowed to do. We're allowed to interchange two equations. We're allowed to multiply by a non-zero scalar constant. on both sides of one of the equations, and we are allowed to add a non-zero multiple of these two equations to each other. So basically, we multiply an equation by a number to scale it up or down, and then we can add or subtract two equations from each other. I think it's easiest for us to just jump right in and look at working through a problem. So let's do an example. In this example, we are given three equations, each with three variables. We want to solve this system and find our unique ordered triple solution. So as we said, we're going to use the elimination method twice, which means we're going to eliminate the same variable using two of these three equations twice. Now I can pick and choose the two equations I want to use. They're all interchangeable, but I'll have to use two different equations twice. We have three options for variables to eliminate. We can eliminate x, we can eliminate y, or we could eliminate z. To me, z is the most obvious or the easiest choice because dealing with the first and the second equation here, I could just add these two together and I would eliminate z because those are opposite coefficients. And then I could use the red and the green, the top and the bottom equation, multiply the top equation by a positive 2. That would give me a negative 2 here, and 2 plus negative 2, that would go away. So that's probably the easiest route, but they're not always going to be that easy. So I'm going to choose to actually eliminate x. So we see some more of that scalar multiplication. So if we deal with the x's, and say I'm looking at just the first two equations, what scalar non-zero value should I multiply this red equation by in order for these two variables to cancel? And if you said negative 2, you're right. So I've gone ahead and I've labeled my three equations, equation 1, equation 2, and equation 3. Those numbers are in circles. That means they're identifying the three equations. And my first step is going to be to multiply equation 1 by the scalar value negative 2 and add that to equation 2. So what would that look like? Multiplying the first equation in red by negative 2 all the way through, that would give us negative 2x minus 4y plus 2z equals negative 10. Now I've gone ahead and written equation 2, my blue equation, below it, and now I'm going to add them together. So that's going to give me 0x. I have minus 8y plus 2 plus 1 is 3z equals negative 10. This is one of my new equations. I'm going to call this equation 4. So I've rewritten equation 4 up here. We have negative 8y plus 3z equals negative 10. So notice equation 4 only has two variables, y and z. So in order to solve this, we need another equation, that will be equation 5, with also those same two variables, which means we need to figure out how to eliminate x again. I'm going to look at using equation 1 and equation 3, the top and the bottom equation. Since my x in equation 3 has a coefficient of positive 3, I need to multiply the top equation, equation 1, by negative 3. So this is our second step. So again, I'm going to multiply that top equation by the value negative 3 and add it to the bottom equation. And when I multiply my top equation by negative 3, that gives me negative 3x minus 6y plus 3z equals negative 15, doing that distribution of negative 3 4 times. Now, I've listed equation 3 below it, and I want to add these two equations together. So when I look at adding these together, again, just as we set this up, those x's should cancel. Negative 3x plus 3x is 0x. And I'm left with negative 4y plus 5z equals negative 12. Now we have a fifth equation, right? So negative 6 plus 2 is negative 4. 3 plus 2 is 5. Negative 15 plus 3 is negative 12. So again, I've cleaned up my screen. Now for just a minute, we're going to forget about equations 1, 2, and 3, and we're going to focus on solving 4 and 5 for the variables y and z. We're going to solve a system of equations in two variables. So now you can see I've created a workspace for us. I've written equation 4 and equation 5 just down below so we have some space to work. I need to choose a variable to cancel. To me, since 8 is a multiple of 4, I think canceling y makes more sense. I'm going to choose to multiply this bottom equation by the scalar value, which is non-zero, of negative 2. Multiplying by negative 2 is going to make this a positive 8, and then we'll have opposite variables. So what that will look like is this. So negative 2 times negative 4 gives me positive 8. Negative 2 times 5 gives me negative 10z. Negative 2 times negative 12 gives me positive 24. At this point, I'll add these together, engineered so my y values cancel, and I have negative 7z. 3 minus 10 gives me negative 7, and negative 10 plus 24 gives me positive 14. Dividing both sides by negative 7, I determine that z is equal to negative 2. So here is 1/3 of my answer. I also need to find my y and my x value. Well, at this point, we're just going to work backwards. Using z equals negative 2, I can plug that into either equation 4 or 5 and find z. Plugging z equals negative 2 in for z in equation 4 gives me negative 8y plus 3 times my z value, negative 2, equals negative 10. Simplifying this, I have negative 8y minus 6 equals negative 10. I'll add 6 to both sides of the equation. Negative 10 plus 6 is negative 4. Divide by negative 8 on both sides of the equation. I have negative 4 over negative 8, which is positive 1/2. So now we know that y equals positive 1/2. All we have left to determine for our solution is what my x variable is going to be equal to at that point of intersection. I can choose any of these three original equations to plug my y and z value in to find x. One thing I notice is I have a fraction, so I just want to make sure wherever or whichever equation I'm choosing to plug y in, that the coefficient is a multiple of 2, so that fraction goes away nicely. I've chosen the first equation, equation 1, so that is x plus 2 times y, which is 1/2, minus z, so minus negative 2. Simplifying this, that is x plus 2 times 1/2 is positive 1, plus 2 equals 5, x plus 3 equals 5, and subtracting from 3 on both sides, we end up with x equals positive 2. Therefore, my x, y, z ordered triple solution is 2, 1/2, negative 2. And this ordered triple should give me a true statement in each of my three original equations. So that's how we solve a system of equations in three variables. And this is a very important skill for you to have moving forward in your mathematical career, being able to determine what those missing variables could be. We could also have solved this using matrix mathematics, linear algebra. You will see some of that in the homework, and you can use your calculator to help you, but I really want to make sure that you know how to do this by hand. And once you get practice, get a couple of them under your belt, it's really not that hard. It's just repetitive. So good luck, and email me if you have any questions.